Okay, so what we've done so far is we've created a space for our projects to go in Box. And then we looked at, oh, we have this GitHub thing where we can manage repositories of code. And I have a GitHub classroom that lets me distribute code to you. All right, so the first two projects that we're distributing are fully running Vivado Verilog designs that you can run in Vivado. Okay, so what I'm going to do here is I'm going to click on Vivado to let it start to run. So while we wait for that to invoke, the next thing we did was you accepted the assignment, which created a repository in the GitHub Classroom. So from there, you use VS Code to clone that repository. And when you cloned it, you put those files in the Box folder. All right, so now you're sitting there in lab, you just go to Box and you got the folders ready to use to import into Vivado, and you can implement your design that way. Okay, so several steps there. It's going to take a while for you to wrap your head around all that. There's a lot of thinking involved at first, but by the time you reach the end of the semester, this workflow will be old hat to you and you'll be able to do it really quickly. Okay, so we've got Vivado up and running, and so what we're going to want to do is create a project. Okay, all right, so create a project, and this is a little wizard that helps you go through this. The first thing we're going to do is have the project name. Okay, so notice that I've already got this searched. Okay, so we had set up Digital Logic Lab, we said Lab 1, and then we have this repository that we cloned using VS Code, and I'm going to create a new Vivado project at the lab at the same level as this repository. So I'm going to click on this, and then I'm going to name that project Vivado. I'm going to name it Vivado 2 because you might have seen that I had a Vivado 1. It was a false start where the video camera didn't start, and so I had to redo this. It doesn't matter what you call the project name. I usually just go with the default that it comes with there, but I just wanted to show you that you can name it whatever you wanted. Okay, so this was set up in Box. This is the project name. We're going to have a Vivado project to help us target hardware. All right, so the next thing you'll do, you'll always have an RTL project, and we don't specify the sources at the project setup time. We import those later with this workflow. Okay, so hit next. All right, from there, we need to choose the target board, and for this class, you would have checked out a Basis 3 board. All right, so we click over on this, next, finish, and we will have the project ready to go. If you forget that Basis 3 board step, you'll get to the end and things won't work, and you're like, what's going on? And so you can always look at this project summary, and it gives you the overview of how you've had this set up, and you should see Basis 3 board here if you've done it right. Okay, so at this point, we haven't defined a top module or anything. We don't have any sources in the project. Okay, but it's ready to go. Now, what you should know about Verilog is that there's two kinds of files. All right, there's files that hold modules. Modules are the building blocks for Verilog, and some of the modules are design sources. All right, so you have a design that you want to build up, and then some of them are simulation sources. So you have to control how you simulate the design, and that takes code as well. All right, so it's important to know which is which. And so we have this file structure set up in the repos that make it clear which ones are the design files and which ones are the test bench files. Okay, so we're going to start with design files. Hit a plus button here, and you can see it's got a radio button that says add design sources. It's important to get that straight. Design sources need to go into design sources. I'm sorry, design files need to go to design sources, and test benches need to go to simulation sources. Don't get those mixed up. All right, so then we can hit the plus button and we can add files. Now, this is where our cloned repo is. All right, so we have a folder set up that has our files in it. All right, so I click on that. RTL stands for Registered Transfer Logic, okay? And so that's the design part. So you see I have two design files here. We'll talk more about wrappers and stuff, but not today. We're just trying to implement the design as it's written without having to do any coding ourselves. Okay, so that puts in the design part. Okay, the next thing you want to do is simulations, because I'm going to show you how you can simulate the design working. Okay, and so we hit plus, all right, and we're going to add some simulation sources, add files, and that's going to be in a different directory, so we can move up. TB stands for test benches. Okay, you might think it was Sims, but Sims is typically where the outputs go. All right, so this would be either test benches, or spelled out, or TB. Okay, so we're going to open that, and you see I have one test bench there, and I'm going to put that into the project. Okay, then it turns out, we're going to learn more about this as we go, but it turns out you have to have something that tells, it's the interface between the design that you create and the pin numbers on the board. So these are called constraint files, and I've already put some of these in. All right, so we're going to add constraints. By that I mean we're going to add files. You can either do here or here. Okay, and I've already put these into a folder. All right, you'll have to download these into a folder from Canvas, but I've already done that. Okay, and so you see our design is going to use switches on the boards, and it's going to use the LEDs. Okay, so I'm going to hit the command button on my back, the control button. That's not it. I forgot I'm on a PC, virtual PC. So I'm just going to do it this way. Add them one at a time. Switches. And LEDs. I'm not using the buttons or the clock or anything else. So those two things. Okay. So at this point, we have our design into the project. We have our test benches into the project. So next, this in Vivado shows you the workflow. So you're going to add stuff in, and then you're going to run a simulation, okay, to see if it works. So we'll hit run behavioral simulation, and this takes a while. It's going to run. You scrub through this step. Okay, so out comes some waveforms, and oh, it looks like it messed up. So anytime you see blue and red, things are not working right. Okay, so what I want to do is go back to the sources, okay, and many times Vivado will figure out what the test bench is, but you notice here what's in boldface and what's not. The wrapper is in boldface, the test bench is not, and I wanted to run the simulation. The simulation is the test bench. Okay, so that's a common mistake. So I'm actually kind of glad it happened so that you can know what to do. So you will click on this, right click on this, and we'll set this as the top. Okay, that means that's what I want to run. Okay, so now you see that's in boldface, and let's rerun that simulation. Okay, the process, these are good to run, run across these errors. This process can't happen because it's being used by another process. We already had a simulation kind of running, so let's close this and start over. All right, so rerun the simulation. Okay, so I think I mentioned in one of the other videos, this is a very simple design. It's just a logic function that's supposed to put a 1 anytime there's a prime number. Okay, so I've got this set up where you can look at the waveform. Okay, and so one thing that you need to do to make this waveform look better is you scale it. All right, so I have a test vector that's actually assigned to A, B, C, and D. All right, so if A is all zeros, 0, 0, so if I click right here, you see A is all 0, 0, 0, 0. This test vector is 0. Test vector is assigned to A, B, C, and D. Okay, and then Y is the output. So 0 and 1 by definition aren't prime. But 2 is a prime number, 3 is a prime number, 4 is not, 5, so forth. So you can see this is working. All right, so that's the simulation part of this. So once we have that, we can then go to the synthesis. But before we do that, I wanted to show you something. This is kind of cool. So you can click on this button and look at the schematic that was generated by this design. Okay, so we're going to hit OK. And there's a bunch of connections to OR gates and AND gates that show up to make a prime number detector. You could look into that and investigate that for yourself. But I wanted to show you the schematic because it's kind of cool to look at these. And this is actually a good debugging step too. When things don't work right, often you can look at this schematic view and see, oh, that signal's connected to the wrong place or what have you, and be able to detect what's wrong with it and debug your circuit. Okay, so notice I call it circuits because that's what you're doing. You're simulating a circuit in hardware. All right, so this is showing we have switches connected to A, B, and C, and so you'll see when you run this on the board, you can mess with these switches, put the hex equivalents of A, B, C, and D, and get the outputs showing up at the LED. You can zoom in. This says this is a logic function. You can zoom into this logic function, rescale it right here, and you see it's a bunch of AND gates and OR gates. Okay, I don't want to get into too much detail, but at this point, you've run the simulation. Next, what you need to do is synthesize this design into hardware. All right, so there's a synthesis step, and so that's got to happen. So it's going to run, and you can check what's happening up in this upper corner. It's running the synthesis, and most of these steps take a while. The bigger the design, the longer it takes, but there's a certain minimal amount of time that even with a really simple design, it's going to take a little bit of time to run through these steps. Okay, so you want to be a little cautious and make sure you don't, try to go too fast because you can waste a lot of time having to redo things like synthesis and implementation. Okay, so if you're listening or watching this, you can scrub through for a few seconds. This is running on a Mac, so it's it's emulating the software, so it actually runs a little faster in the labs on original PC hardware. Okay, so it finished that, and then it gives you a hint on the next step. You can see if you follow this, the next step would be to run the implementation. Okay, so we did the synthesis. Now we do implementation. That takes a while as well. Okay, so I finished the implementation. And so the next step, I'm not sure why it defaults to this, because the next step is to generate the bit stream. Okay, so we'll hit OK. And the bit stream is, I think of that as a bunch of bits, zeros and ones, that tell what the connection should be on the FPGA. We'll talk more about the internals of an FPGA as we go through the course, but it's making the right connections to implement the hardware design. And so once you finish jittering the bit stream, you'll open the hardware manager and load that onto the board. Now, I'm running this from a Mac. This particular step, this opening of the hardware manager and connecting to the board, doesn't work on a Mac, so I'm going to leave that step for the time that we have in the lab. But once you get to the bitstream part, things are pretty straightforward. It's really pretty quick to implement that on a board. Okay, so it says the bit stream was generated successfully. You can open the hardware manager. It's going to fail for me because I don't have hardware connected to the system. But from there, you can look within your file space. So let me do that. Okay, so if I look within the project, where's Vivado 2? There's lots of different files that are created, okay? And so we are doing runs, we're doing an implementation, and so you see there's going to be a lot of files generated. And this is the wrapper, okay? So that's the file that you need. You load that onto the board, and you should be good to go.